Great. Well, thanks very much, everyone. And staying with the environmental theme, we move on to looking at how the impact of climate change may affect developing states. So GWP have been working with the Government of Samoa to demonstrate the importance of flood hazard mapping in vulnerable island locations. Please welcome to the stage Marc. Thanks very much.
Hello, good afternoon, everyone. So my name is Marc Girona-Mata, and I work at GWP Consultants. We are based in Oxford, and we do earth and water resources consultancy. And today I want to talk about some recent experience that we had doing flood hazard mapping in a small island developing nation using GIS-based geomorphology analysis and also LiDAR datasets. So basically, just to provide you with some context within the project, the approach that we actually developed for this project is entirely based on geomorphology, although the aim is to map flood hazards. And we did that using ArcGIS and also LiDAR datasets. This approach was developed and piloted in Samoa as part of 2 different projects, and the ultimate deliverable was to produce national and district scale flood hazard maps for the entire country. So just so that you more or less have an idea of the 2 projects that we were part of, this methodology was applied in 2 different projects, as I said, that had a common client, and this was the Government of Samoa. And the first project was financed by the Adaptation Fund and implemented by United Nations Development Program, and it was called Enhancing Resilience of Coastal Communities to Climate Change. And the second one was under the Pilot Program for Climate Resilience, PPCR, and it was implemented by the World Bank. And we were involved in both projects as one of the consultants. We're there at the bottom, GWP Consultants. It's important to note that both UNDP and the World Bank were the ones that procured a LiDAR survey for the entire covered country of Samoa. So although Samoa is a Pacific island and is a developing nation, it has LiDAR coverage for the entire country. And so they were obviously very keen to utilize this powerful data set that, although it was procured 3 or 4 years ago, and the actual LiDAR survey was completed 3 or 4 years ago, it hadn't been used until this project. So, okay, as I said, the case study, or the study region, was Samoa. Samoa is a small island developing state, or it's considered a small island developing state. Is a set of volcanic islands in the Pacific Ring of Fire. And one particularity of Samoa is that it's very prone to water-related hazards, these being tropical cyclones and also tsunamis from time to time. You can see there a map of Samoa. It's a group of 3 or 4 islands, 2 of them kind of big, covering an extent of 3,500 square kilometers, and 2 of them that you can barely see in the middle. Samoa is a beautiful country, as you can see in that picture, in the upper picture, but it's also very heavily devastated several times, even several times each decade, and sometimes several times each year, by these tropical cyclones that basically swipe everything that they encounter, and they mobilize a lot of sediment and debris and cause a lot of damage. Another interesting point about Samoa is that there's a dichotomy in data availability. So on one hand, they have a severe lack of data relating to hydrometry or hydrometeorology, but on the other hand, they have LiDAR coverage for the entire country. So that's also an interesting aspect. Very briefly, the data that we use and the methods that we use for this project. The data that we use, basically what we used is high resolution terrain morphology data. and that is the 1 meter resolution LiDAR-derived digital elevation model. We also used aerial imagery that was captured at the same time when the LiDAR survey was completed, and this was also very high resolution. But we didn't use any of the data. So we didn't use rainfall or flow or geology information for this flood hazard mapping exercise. And the methodology, as I said, we used geomorphological analysis techniques, GIS-based, using ArcGIS, and what we used is the spatial analyst and 3D analyst extensions and the tools that are included in those extensions, so basically terrain processing and hydrological routing tools. And then we kind of completed that with a field campaign, and that was to validate the method and the results of our work. And for that, it's worth mentioning that we used the ArcGIS Collector app, which really helped us in both completing ground surveying, topographic ground surveying, to validate the LiDAR dataset, but also to populate a drainage infrastructure database. So we basically went along the coastal road of the country, which is the place where all the important infrastructure is placed, and we collected all the district level drainage infrastructure, like bridges and forts and big culverts, and all those conveyance structures where flooding occurs in times of tropical cyclones. And we also used this collector app and the field campaign to verify the GIS products that we had developed. In this slide, I just want to show you on the left-hand side, you can see the aerial imagery that was captured as part of the LiDAR survey. And then on the right-hand side, you can see the classified LiDAR point cloud. It's just to illustrate a little bit, what was the product that we used. So the classification was already completed by the contractor that undertook the LiDAR survey and also classified the data, but we did some quality control on the data to see whether or not it was fit for purpose. It was generally fit for purpose, although in places where Samoa is a very densely vegetated country, and in flat places close to the coast where vegetation is very dense, we saw that this could compromise the accuracy of the digital elevation model that was produced from the LiDAR dataset, and so that's one thing that I will briefly mention afterwards. But in general terms, the LiDAR digital elevation model was fit for purpose. And now here you can see again on the left-hand side the aerial imagery, and then on the right-hand side the digital elevation model that was produced from the LiDAR. Now, moving into the methodology and the ArcGIS routines that we used to do the analysis. Here, I just want to mention that so the different colors correspond to different categories. So in blue, you see the model inputs, the data that we used to produce the flood hazard maps. And although you can see 4 or 5 different blue boxes, the actual data, the only source of data that we used for to map, flood hazard is the LiDAR dataset. The others correspond to either the extent of the country, or in the lower diagram, it's really just some intermediate products that we used as an input for a second model. But basically, all this approach is based on LiDAR morphology data. Before I move into results, I just want to mention that this work has a lot of limitations, basically because it's based on a single source of data, a very powerful, but just the one and only source of data. And so I want to outline these limitations because I think it helps then understanding the results and the conclusions of our work. So one of the main limitations is that although the LiDAR digital elevation model is very accurate in some places, it might also be not be that accurate in some other places, just because as Samoa is a very densely vegetated country, sometimes the LiDAR cannot really penetrate all the way to the ground, and this causes that the density of ground point in some areas, it's so low that if these areas are really flat, the hydrological modeling or the hydrological routing in ArcGIS sometimes doesn't lead to very accurate results. So that was one of the limitations. Another one is that in the upper part of Samoa, Samoa is a volcanic island, and there's persistent cloud cover in some of the areas. So the guys that undertook the LiDAR survey couldn't really capture all the ground, and some of the country extent was actually covered instead of LiDAR, was covered by SRTM data. These were few areas in the country, but obviously SRTM data is a 30 or 15 meter grid, and it's much lower resolution, which causes the quality of the products in those specific areas to be much less. Then, as I said, this methodology focuses only on LiDAR data, and it therefore disregards many other factors. And this responds to basically two reasons. One is a lack of data availability and or reliability in the country. And the other one is that we needed a simplistic approach, which was cost effective and which basically mapped flood hazards at the district and national scale consistently for the entire country. The fourth limitation is that results were difficult to validate because of the lack of data and also lack of historical observations. So now, moving into results, I'm just going to outline basically two types of results. First, I'm going to show you what deliverables we produced for the project. And then I just want to mention two very interesting insights that we found during this project. So in terms of GIS deliverables, I'm going to talk about some simple catchment metrics, and then fluvial and coastal flood hazard products, and then briefly mention the drainage infrastructure database that we captured during the field activities. And then I just want to mention these. We identified subsurface cavities. So these are the so-called lava tubes, which are like underground rivers. And we think that LiDAR has a lot of potential to capture these subsurface cavities, especially in places where these have collapsed. So you have sort of sinks, small sinks, that tell you that over there you have an underground river. And then also the potential for risk mapping and risk communication strategies that LiDAR and ArcGIS can provide. So, okay, moving into the deliverables. The first deliverable that we provide them with is simple catchment metrics. On the upper diagram or map, you can see basically just the catchments colored by catchment size. Now, this is a very simple deliverable, but it turns out that they didn't have such a map available because they had always worked with SRTM data or with other topographical sources of data that they had captured themselves. But basically, we could refine the catchment delineation that they had, and that is probably one of the most useful resources that they will have. And we also used other metrics, other simple metrics, to further develop these catchment categorization maps. And for instance, in the lower map, what you can see is catchment size combined with the length of the coastal road that intersects the catchment at the outlet of the catchment when it goes to the sea, and this. It gives an idea of the shape of the catchment and how much water will it concentrate in that point of conveyance. Either sometimes it's a bridge, sometimes it's a fort, but it basically gives an idea of which catchments might be more prone to flooding and where the consequences might be more devastating. Then on top of that, we also delivered some more detailed fluvial flood hazard products. And here you can see different labels, and these correspond to different zones. I'm going to focus on the inner one, the primary surface water routes. To define these fluvial hazard zones, we use geomorphological features like slope and also the contributing area that's being collected, so basically the catchment area that's being collected at each point of the stream. And we also used something called the stream order. That's the number of streams that basically join upstream of this point. And all of these metrics combined give an idea of the potential hazard that water can have in this particular point. So on the left-hand side, you can see the aerial imagery, and then on the right-hand side, it's a slope map overlain by the different fluvial hazard zones. The other fluvial hazard zones are just buffers from the inner fluvial hazard zone, and these were zones that were a request of the government, and they will be used for spatial planning and other planning procedures. And I just want to mention, this is the coastal flood hazard products that we developed. Basically, these are very simplistic. They are just based on elevation, because the lack of data, of hydrometric data and other sources of data makes it actually impossible to really go on a very detailed hydrodynamic modeling exercise. And what we basically did here is determine different elevation bands that give them an idea of how far inland do these elevation bands reach. And basically, these are meant to account for the sea level rise that occurs during tsunamis, but also during tropical cyclones. So one of the devastating effects of tropical cyclones is that on top of the winds and rainfall, there's also like a sea level rise that can be as great as 5 meters, and therefore, there's a combination of events there that really causes a lot of damage. So these will hopefully help them planning and locating key infrastructure in the right places. And then we also delivered a byproduct called zones of uncertainty, and these basically accounts for potential digital elevation model inaccuracies due to persistent cloud cover, or also flat and densely vegetated areas where our routing and our products might not be that accurate. And it was important that they were aware that there were zones where they cannot heavily rely on these products. Here, I just want to mention a couple of things related to the field campaign and also the product delivery. And this is how we use the ArcGIS capabilities or suite of products to really streamline our process and also the product delivery. So on the left-hand side, you can see a couple of images showing a bridge. And that's just to illustrate that, as I said before, we use the ArcGIS Collectors app to capture all the drainage infrastructure along the coastal road. In 5 weeks, and we were 2 of us doing this, we collected more than 700 features, drainage infrastructure features. We basically covered all the country, and this was only possible because we were using the ArcGIS Collectors app, and just by the click of a button, you capture one point at the right location. There was a very good signal in the entire country that really helped us, but basically, otherwise, manually having to, even if you have a GPS, but you have to start combining, manual entries with GPS tracks. It really makes it difficult to streamline your process, whether with the ArcGIS Collectors app, we were able to just fly through it. And then the other thing is that we also provided them with all these deliverables in an ArcGIS Online platform. And this really, we think it has the potential for really communicating risk and enhancing the use that they will make of these products much more, rather than just delivering a report and then a CD with the result and the GIS layers. If you can add them into an online tool, and everyone is able to access this tool, and without having ArcGIS installed in their computer, because some of the people that might be interested in these data sets are high-level government officials, and they might not be GIS users. But with these online platforms, you really kind of enhance the use that they will make out of this data. Now, just to be finishing up, I just want to mention these lava tubes. Basically, what we found is that in Samoa, although there are a lot of rivers which carry a lot of water, because it's a volcanic island, historically, there have been subsurface cavities that have been developed and eroded by rivers, and these cavities have collapsed at some point. And most of these cavities are completely unknown because they are up in the catchments, and no one lives there, and there's so much vegetation that no one knows that they are there. But with the LiDAR dataset and with the LiDAR digital elevation model, you really see those cavities. You can see that there are 3 cavities that are consecutive, and these are 3 collapsed points of this subsurface river. And basically, a little bit far downstream, I'm talking now the upper left image, you can see that there's a river channel that appears out of nowhere. That's just a discharge from the lava tube. And so we think that in this regard, LiDAR datasets and GIS analysis has a lot of potential for really identifying these features that really might be even aggravating the flooding consequences, because basically people cannot foresee, if it's raining up there and they don't know that there's a lava tube that at some point is discharging to this river system, they cannot really understand the river system unless they also take into account these hidden cavities. And then the last thing I want to mention is that we think that basically now we've mapped hazards. We have produced preliminary flood hazard maps, but we think that LiDAR datasets and also GIS analysis has the potential to bring hazard into risk. There are many definitions of risk. I've just kind of put one here, which is taking hazard and then times vulnerability times exposure divided by adaptive capacity. We'll probably look into this further in the future, but basically what we want to see is how many of these other variables can be defined using LiDAR and GIS analysis. Here I'm just showing a map of a case study that we started to investigate on this risk perspective. But basically, to wrap up, so the lessons learned from this project is basically that the piloted approach that I have just explained is very cost effective, obviously when LiDAR data is available, and has led to consistent results across the study region. It also has enabled the identification of high hazard areas that probably require further modeling efforts, but at least then they can focus on these areas. And finally, it has led to easy to interpret results. That's probably the most important one. And this has the potential for improving risk communication strategies and to raise awareness in those countries. And then just some recommendations. We were thinking of probably introducing rainfall data into this methodology and analysis, probably using ArcGIS routines and the unit hydrograph theory. Or also we were thinking of further developing this risk mapping approach, also using ArcGIS routines. Also further looking into risk communication strategies, because we think that's a key one. And finally, assessing the role of these lava tubes or subsurface cavities, the role that these have in the rainfall runoff modeling and routing. And we think that both LiDAR and ArcGIS have a very big potential for all these future steps. Thanks very much. And I don't think we've got time, but I'm happy to answer any questions after in the break.